What if scientists found something that literally shouldn't exist, and they have the data to prove it? Right now, gravitational wave detectors picked up a signal from an object sitting in what physicists call the mass gap. It's too heavy to be a neutron star, but too light to be a black hole. So what is it? In this video, we're breaking down exactly why this object breaks the standard model of stellar evolution, and why the ripples in space-time that revealed it don't lie. Let's get started. There's a stretch of the cosmic graveyard, between 2.5 and 5 solar masses, where nothing should exist. No neutron star, no black hole, just empty space in the mass spectrum. So when something showed up there, physicists genuinely didn't know what to call it. To understand why that's such a big deal, you need to know what happens when a massive star dies. When a star runs out of fuel, the core collapses under its own gravity. If the core is heavy enough, you get a black hole. If it's not quite that heavy, the collapse stops partway, and you get a neutron star instead. This incredibly dense ball of tightly packed neutrons, roughly the size of a city, but heavier than the sun. Those are your two options. That's it. Neutron star or black hole. There's no third category, at least not one we've confirmed. The problem is the numbers don't leave any room in the middle. Neutron stars max out around 2.5 solar masses. Push one above that, and the internal pressure just can't hold anymore. It collapses into a black hole. But on the black hole side, the lightest ones we've actually detected come in around 5 solar masses. So between 2.5 and 5, you've got this gap where neither type of object shows up. And for decades, the data kept confirming it. Think of it like a height restriction at an amusement park, but flipped. You can't be between 2.5 and 5 feet tall. You're either shorter or taller. Except this isn't some arbitrary rule someone made up. It comes directly from the physics of how stellar cores behave under extreme pressure. The gap is supposed to be a real physical consequence of how stars die, not just a hole in our data collection. The theoretical explanation for why involves something called pair instability supernovae. Basically, in certain mass ranges, when a stellar core collapses, the process becomes unstable. Gamma rays inside the core start producing electron-positron pairs, which drops the pressure, which causes a partial collapse, which triggers a runaway explosion. The result is that some cores in that mass range get partially blown apart rather than collapsing cleanly into anything. So instead of leaving behind a compact object, the explosion scatters most of the mass into space, and nothing sits in that middle range. And the observations back this up for a long time. Decades of X-ray binary studies, pulsar timing measurements. Researchers kept finding neutron stars below the gap and black holes above it. So the mass gap wasn't just a theoretical idea. It had real observational support behind it. There were a few hints that the boundary wasn't perfectly sharp. Some neutron star mass measurements crept up to 2.1, even 2.2 solar masses, closer to the gap than earlier estimates. But nothing actually landed in the middle. The model stayed intact. So going into 2019 and 2020, the mass gap was considered one of the more reliable predictions in astrophysics. Not a hot topic, not something researchers were actively debating, just a known feature of how stars end. The gap was there, the data supported it, and nobody expected that to change. Then LIGO picked up a signal that put something right in the middle of it. And the mass gap stopped being a settled question, because whatever that signal came from, the physics we had couldn't explain it. Gravitational wave detectors don't take pictures. They don't collect light. They measure the actual stretching and squeezing of space itself, changes smaller than a fraction of a proton's width. And in August 2019, the detectors at LIGO and Virgo caught something that made the physicists running the analysis go back and check their work. The event is called GW190814. Two objects collided roughly 800 million light-years away. One was clearly a black hole, coming in at about 23 solar masses. The other one was the problem. It measured around 2.6 solar masses, sitting right in the middle of that mass gap we just talked about, right where nothing is supposed to be. Here's the thing about gravitational wave data. You can't fake the mass. The frequency and rate of change of the signal encode the masses of both objects directly. It's not an interpretation. It's not an estimate based on how bright something looks or what color light it gives off. The math gives you the masses, and the masses said 2.6 solar masses. That's just what the numbers said. So here's how that actually works. When two massive objects spiral into each other, they warp space-time as they move. That warping radiates outward as waves, ripples moving through the fabric of space at the speed of light. When those ripples reach Earth, they stretch space in one direction and squeeze it in another. LIGO's detectors measure that stretch and squeeze using lasers bouncing between mirrors that are 4 kilometers apart. The change in distance they're measuring is almost unimaginably small, but the detectors are sensitive enough to catch it. What tells you the masses is something called the chirp. As the two objects spiral closer together, the frequency of the gravitational waves rises. It literally chirps upward in frequency right before the collision. More massive objects produce lower frequency chirps. Less massive objects chirp higher. The relationship between the chirp and the masses is something LIGO had already confirmed against Einstein's predictions multiple times before this event. So the instrument works, and the analysis works. That part isn't in question. So what is the 2.6 solar mass object? It's too heavy to be a neutron star under any model we currently have. Even the most exotic proposals, ones involving strange quark matter packed into the core, push the neutron star mass ceiling to maybe 2.5 solar masses. And it's too light to fit the pattern of black holes we've actually detected. It just doesn't belong to either category. The research team sat with this for months before they published anything. They ran alternative analyses, checked for systematic errors, looked hard at whether the signal could be explained some other way. It couldn't. When the paper came out in the Astrophysical Journal Letters, the conclusion was essentially, we don't know what this is. There are two directions researchers have gone with it. One is that this is the heaviest neutron star ever found, which means neutron stars can survive at higher masses than our models allow, which means our understanding of dense nuclear matter is wrong. The other is that it's the lightest black hole ever found, which means black holes can form at lower masses than we thought, which breaks the stellar evolution models differently. Either way, something in the physics is off. The gravitational wave data itself is solid. What it's pointing at is a gap in our understanding, and that gap goes deeper than just the mass of one weird object. So here's where we actually land. The mass gap was backed by theory and decades of real observational data. GW190814 didn't just challenge that. It dropped a 2.6 solar mass object right in the middle of it. And we still can't fully explain it. That's not a problem with science. That's just how science actually works. LIGO and its partner detectors are still running right now, still collecting data, and researchers are actively hunting for more mass gap events. The more signals we find, the clearer this gets. So subscribe and hit the bell so you don't miss it when the next one drops. Thank you for watching, and stay tuned.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.